Okay, so I'm Sean. I'm going to talk today about the changes we're making to the way partitioning works in Legion. And so I'll start with a little overview of partitioning, why it's important, and what the choices are in this space. A little brief digression on the difference between index spaces and logical regions. We've talked about it a little bit, but I want to make sure that the difference between them is clear in your minds. Then I'm going to talk about the operations that are available in the new dependent partitioning framework that we are switching to. I'll talk a little bit about performance, the current status of this, and then a handful of related features. As with many things in Legion, this is sort of a hierarchical structure. So partitioning is the keystone that's going to enable a couple other related things. And I'll touch those briefly. OK, and as with the other talks, feel free to interrupt me as we go to ask questions and stuff. OK, so let's start with partitioning. As we've already mentioned, partitioning is essential in Legion applications or in Regent applications for exposing parallelism and also limiting data movement. Right? We want to be able to talk about things that are disjoint from each other and to determine when two tasks are independent and can be run in parallel. And we also want to be able to say what data we're going to access so that we only have to move the data that's needed for that task. And so we want to be able to precisely describe the data that's used by a task. The closer we can get to the actual set of data that's used, the more parallelism we're going to expose and the more data movement we're going to avoid. And so one way to think about this is we want to maximize the expressivity of what you can describe in your partitioning. When you cut boundaries between things, you want to be able to do it as expressively as you'd like. But on the flip side, we also want to be able to compute and work with these partitions as efficiently as possible. And in particular, optimization, either whether in the compiler or in the runtime, requires the ability to analyze the operations that are being performed. If we can't analyze them, we can't optimize them, and quite likely it's not going to be as efficient as we would like. And as is common in the computer science world, there is an unavoidable trade-off between these two things. You can't have a perfectly expressive and perfectly analyzable setup. You have to choose some point on the spectrum and make the corresponding trade-offs. So let's talk real quick about the two extreme cases that are the most commonly used cases. So the one extreme of this spectrum is simplicity. And this is actually the way that almost all languages go. So pretty much all the PCAST languages choose to provide only very simple array-based distribution methods. Right? You can have any distribution you want as long as it is block cyclic or block cyclic. And these work great for distributing arrays across a large machine. They're very simple for the programmer to describe. They're very simple for the compiler to verify the consistency of two different distributions. And they're very simple for the runtime to implement. These are all good things. On the flip side, there's basically no support for irregular or even semi-regular data structures. You basically have to mash them into these existing distribution methods. There's no support even for irregular partitions of structured data. Again, you have to find some way to make it look like either a block distribution, a cyclic distribution, or a block cyclic distribution. And finally, these distributions are tied to the exact mapping onto the machine, so there's no support for aliased or multiple partitions either. So again, there's pros and cons. This is one place you can be on the spectrum. In particular, Legion. With Legion, we chose to go to the other end of the spectrum. So the old Legion partitioning, as many of you are familiar, used a general purpose coloring object for basically all partitioning operations. And this was great because it meant an application could color every element any way it wanted. You had maximum expressivity. We supported arbitrary irregularity in the data and the partitioning. And we had support for alias partitions for multiple partitions. So we've chosen to veer on the side of expressivity. And as you might guess, we intentionally chose to pay the price in terms of efficiency in the short term. And these prices actually show up in a number of different ways. As some folks in the room will happily attest to, there is significant programmer effort to describe even fairly simple partitions in the old setup. You had to build a coloring even for something that was just a fairly regular partition. Once you had multiple colorings, there was no ability for the compiler to check that the related regions were even partitioned consistently, which could be the source of all sorts of interesting runtime bugs. There was a high overhead for computing and querying these partitions. And as we'll see in my performance slides, almost all of that overhead was on the application side, so it wasn't something the compiler and runtime could help optimize. And then this last one isn't necessarily intrinsic to the choice of expressivity in general, but our particular implementation of colorings was serial and limited to a single node. And so Alex was mentioning the lack of scalability that we had before. And so this particular last one had to be fixed. And when we were fixing that, we figured we might as well try to knock out some of the other ones as well. So to show an example of what this looked like, let's look at the way our favorite circuit example was partitioned in the old way of doing things. So you've seen this before. We're going to go through it in a tiny bit more detail. In particular, I'm going to show you what the colorings looked like. So we had our nodes and our wires as regions, and we had our intended partition. And so conceptually, we're going to want our private nodes, which has colored like this. We were going to want our shared nodes, which were colored like that, and our ghost nodes, which are colored like that. Note the one that's both red and blue there. Similarly, we wanted a partition of the wires that was colored like that. And then we also had this funny one that Alex was showing you where we made this private and shared split at the top for performance reasons, and it looks like that. And so this is basically what the Legion runtime sees in the old partitioning scheme. It sees 5 different colorings, and it has no idea why the application chose these 5 colorings. There's a bunch of application code that is computing these and tossing them over the wall to the Legion runtime. And let's actually look now at I'm not going to show you the code for that because it's big and ugly. What I'm going to show you is kind of a pictorial version of what was actually going on in that code. And so in particular, what was going on in that code is the code first computes an assignment of nodes to the ranks, if you will. Basically, a general distribution of how it wants the data to be, how it wants the nodes to be partitioned across the system. From that, it decides a way how it wants to assign wires to precise ranks, and it does this by basically picking one of matching it to the color of one of the 2 nodes it's connected to. Once it's done that, it then figures out, OK, from each of my wires, from what nodes can I reach? And so it builds this effective coloring where all the boundary nodes get 2 colors. It then looks at which are the ones that are outside of what I owned. So basically, what's the difference between this one on the right and this one in the middle? And that's basically going to be, it's going to turn into the shared nodes. And that's actually also the ghost nodes there. And then once it's got those, it's going to use, now it's got the distinction between shared and private, it can split our original coloring into the ones that are private for each piece and the ones that are shared for each piece. So that's what's going on behind the scenes. It takes, I don't know, somewhere between 50 and 100 lines of C++ or Regent code to do. And basically, it's just building all these various colorings and then tossing them over to the Legion side. But the key observation here, actually, there's 2 key observations here. First of all, there's this one choice in the center that drove everything. And we're going to call this the independent partition for reasons which will become obvious in a moment. And this is where all the application, all the free will in the application was. It chose how it wanted to do this. And then all these other partitions were all computed depending on this initial partition. So we're going to call them dependent partitions. And we're going to observe that the ways in which they're computed amount to a handful of relatively simple operations on colorings, or on partitions, if you will. And so that was the inspiration for our new model, which we call dependent partitioning. And the idea is this is going to be a carefully chosen middle ground between the 2 extremes I talked about before. And the idea is we still want to allow arbitrary independent partitions to be computed by the application. We believe this is very important for expressivity and handling irregular cases. Although we are going to improve this by, instead of using colorings, we're going to actually use data in a field in a region to capture the intent so that you don't have to build colorings. And we're also, though, going to add to it index-based partitions to cover the simple cases that the PGAS type languages have gotten right for years and years and years. And so these are going to be the 2 different ways we can do independent partitions. Again, maximizing expressivity on one side and simplicity on the other. But then also we're going to provide a set of operations, and critically an analyzable set of operations, that allow you to compute dependent partitions from the other partitions. And the idea is that, for the most part, these are going to be based on either reachability operations or set operations on these partitions. And in addition to some performance optimizations, one of the nice things that's going to come into this is that we're actually going to be able to verify the consistency of these dependent partitionings at compile time. Not only are we going to be able to optimize them at runtime, we're actually going to be able to understand them well enough to do static analysis at compile time. And then for bonus points, by integrating this into Legion's data and execution model, we're going to get all the support we'd like for distributed partitioning, deferred execution, being able to do partitioning in parallel with other computation, and basically all the things that were preventing us from doing either very large problems or problems that required repartitioning over the course of execution. So that's dependent partitioning in a nutshell. I'm now going to take a brief digression and talk about index spaces versus logical regions. The two get used almost interchangeably in some cases, and I want to make it clear how they differ. And so as we talked about before, a logical region is constructed from an index space and a field space. So if I've got this R1 here, the way we built that was by specifying a particular index space, this IS, and a particular field space, FS1 here. But then all of our examples for partitioning, we generally talk about partitioning a region. And so we do this, and we show a region tree here. But partitioning a logical region is actually, right, remember, we're talking about naming subsets of the elements in a region. So what we're actually doing is we're partitioning the index space. So every time you see a region tree like this, know that there is a corresponding tree in the index space from which it came from. And in particular, the operation to partition the region is identically the operation to partition the index space. Similarly, if you have other regions using the same index space, like say R2 here, they also get the same partition. So basically, the tree technically belongs to the index space and is available to all of the logical regions that are used in that index space. And so similarly, if we did another partition in the index space here, that would immediately become available in both the other logical regions. So partitioning is really an operation on index spaces, and logical regions simply inherit whatever partitions their corresponding index space has. So now in the C++ API, there's calls to basically move between the corresponding nodes in region or index space trees. In some cases, you want to talk about just the index space node in the tree. In some cases, you want to be able to talk about the one for a particular region. And so there's calls to go back and forth. Regent lets you do one direction right now. You can use regions any place an index space is needed, but we haven't settled on the syntax that lets you go the other way. That's mostly a matter of sitting down and deciding what it should look like. There's no real challenge to it. But basically, the way to think about it is you'd be able to move back and forth. So sometimes you want to talk about partitioning index spaces because you're going to have multiple regions that are using the same index space. And sometimes you're just going to have one region using an index space, and it's easier just to talk about partitioning the region. But I want everybody to have in their heads that really what's going on here is we're talking about partitioning index spaces with the region as simply a proxy for it. So haven't confused anybody yet, or I've confused everybody completely. Let's go back now to the actual partition operations that are going to be available in the new dependent partitioning model. So as mentioned, we're going to slice these two different ways. We talked about there are going to be operations that are going to compute independent partitions, and there are going to be operations that compute dependent partitions. And there's going to be three different kinds of operations available to us. The first is what I'm going to call index-based operations. And the idea here is these are operations that chop up an index space just based on properties of the index space itself. They're not actually looking at any data in the space. In contrast, there will be field-based operations, which chop up an index space based on the data in the field for one of the logical regions using that index space. And then finally, we're going to have some set operations for doing just direct manipulation of the index spaces themselves. So kind of in the first corner, we're going to have equal and weighted index space partitions to compute independent partitions. And then we're going to have a very important filter operation that lets us use field data to compute an independent partition. And this is basically going to be our replacement for the old style partition by coloring. On the dependent side, there'll be a way to do restrictions of an index space based on the indices themselves. There'll be image and pre-image operations that let you compute reachability. And then finally, the set operations you might guess, union, intersection, and difference let you compute new partitions from old partitions. So I'm going to walk through each of these fairly briefly. And stop me if I go too fast. OK, so equal partitions, hopefully not too scary. We're going to split up an index space into roughly equal partitions. If it doesn't divide evenly, then some get more, some get less. But that's OK. Did you have a question now, or do you want to?
A question about nomenclature? dependent, independent? Why did you use this typology? I'm sorry, I missed it.
Basically, there's going to be a bunch of terms that kind of come from mathematical terminology for functions. The image and preimage are there also. So think of independent variables and dependent variables. Okay. Okay, so when we do an equal partition, we need to say how many pieces we want, and we're going to need to have names for those pieces. So we have a natural construct that gives names to elements of something, and that's an index space. And so the way you're going to say how many pieces you want in an index space partition is you're going to supply a second index space. And we're going to create one subspace of the original one for each point in the second space. So as an example, let's say I've got my index space 1 here with a bunch of elements, and I've got a second index space 2 here with exactly 3 elements, and they're numbered 1, 2, and 3. If I create an equal partition of IS1 using IS2, then what I'm going to get is a partition of IS1 with 3 subregions, numbered 1, 2, and 3, and they're going to have roughly equal numbers of elements in each. Let's assume there's not too many of the dots there. So this is obviously very useful for structured cases, but it's also useful as well when you're doing unstructured stuff. If you're going to compute a partition on the fly, you need some initial partition in order to even be able to have enough space to store things to compute your partition. So often, until you understand what the topology looks like, you need some way of scattering the data across the machine. And so you might use an equal partition initially and then refine it through some algorithm. OK, so that's an equal partition. A close relative of it is the weighted partition. And so this is, as you might guess, is going to split an index space into uneven pieces. So again, here's our index space. And again, the number of pieces is going to be specified by a second index space. So there's IS2 there. But now the difference is that we're going to need to associate a weight with each of the subregions that we're going to create. And so this is application data. And since we want to be incorporated with the Legion data model, we're going to store that in a region. Okay, so we need a weight for each piece specified in a field. And so there's going to be some logical region associated with the second index space. And it may have a bunch of fields. In particular, one of them is going to be some weight field. And let's say here I've got a weight of 2 for index 1, a weight of 4 for index 2, and a weight of 3 for index 3. Okay, and this can be any old logical region. And critically, it can be the result of any computation, any arbitrary computation in the application. You can fill it in however you want. You can run some horribly complicated algorithm for it, or you can just read the answers from a file. We don't care. That's your problem. All that matters is you get the value into the field. And once it's in the field, we do the same thing. We say, OK, well, there are 3 points in the index space, so we're going to make 3 subregions. But now you've given us weights, so now the red subregion is a little bit smaller, the green one's a little bit bigger, and I guess the blue is the same size as it was before. OK, so this is the first example of basically, instead of having extra objects using to provide the initial data, we're going to use index spaces to name the points that we want, and we're going to use field data to provide any additional information about the points or about the elements of the index space that we want to partition. Yeah?
What happens if IS1 is not perfectly divisible, then you have weights?
Yeah, I left out so the question was, what if the IS1 is not a multiple of the sum of the weights, basically? And I left out the word roughly here, but it's the same thing. We round in some reasonably sane way. But we're not going to give you fractional elements, nor are we going to throw an error. So if you want to make it precise, you can. If you want to make it just best effort, then that's fine too.
And why are there dots, on the blue side? Is it because there is an arbitrary number of indices in there?
Yeah, the idea for the dots there was just to give the impression that IS1 might be really, really, really big, whereas in particular IS2 is relatively small. IS2 is naming IS2 is going to be on the order of the number of nodes, the number of ranks you're targeting.
Yes.
Whereas IS1 is the number of elements that you're working on, which may be billions.
Yes, but in that case, if there are many elements, inside, that are not marked here, that are represented by the dots, then the weights would not correspond anymore, right?
Yes, that's correct. Yeah. So
okay.
Imagine in this case the dots are vacuous.
Okay.
For my math to work out. Yes. Okay. OK, so that's going to lead into the more powerful way we're going to use field data to compute an independent partition, and that's filtering. So Technically, that other thing used a field, but it was a field not on the index space we were partitioning, so I lumped it in the index-based category. This one is going to use data for the index space that we're partitioning. So this is going to be a case where you've built an index space, you've actually already got logical regions for that index space with data in them, and you're going to use that data to drive a partitioning. And this is going to be, like, as I said, this is going to be the direct analogy to the coloring-based partitioning from the old way. And so the idea is we're going to use the content of a field as the color for each element. With the caveat that coloring is now basically a point in an index space, remember, because our partitions are all named by index spaces. By letting this coloring live in a field instead of a coloring object, the desired partitioning can be computed in a parallel or distributed fashion, again, any way you want. And you can kind of think of it like, it behaves kind of like a group by operation in SQL. So in particular, again, here's our favorite index space. And now let's say I've got some logical region using that index space and some field x, which has got these values, which are all conveniently 1 through 3. So in the filtering mode, basically, we're going to use the values stored in this field to compute the coloring. And so for each value that shows up in there, we've got 1, 2, and 3. They're effectively assigned different colors. And we're going to use those colors. We see there's 3 of them. So again, we're going to get a partition with 3 subspaces. And we're now going to partition the elements based on those colors. So this lets you compute arbitrary partitions because it's entirely up to you what goes in there. And so this is the equivalent to the coloring before. Yeah?
Is there a null element? Like, can I actually do a sub-filtering where I leave out some stuff from the results?
Yes, and I debated fixing that in my picture, but it broke the continuity with my next pictures. But yes, had there been a 4 in there, so technically, you still need to specify the index space that says we're only interested in 1 through 3. So had there been a value outside of 1 through 3, like a 4 or a 0, that would just not show up in any of the subregions.
But I can't actually make IS1 small. I can't have a logical region that then only does every second element.
No, you absolutely can. Well, I mean, you could actually go as far as you could have a subregion with nothing in it, right? If none of the things match the right value. But for example, one thing you could do, you could have a field that was a Boolean, and then do a filtering operation where you say, I just want the true subset. So you can do some arbitrary computation to decide which are the elements in this entire index space that you care about, and then say, OK, now give me all the ones where that evaluation returned to true, so that I can then iterate over those and do some computation on just a subset of things in an arbitrary way.
All right, thanks.
And that actually leads into my next point, which is right now, in the current version, you can only do this filtering on the raw value. But fairly soon, we have a plan for basically allowing you to do function composition. So instead of just using the value directly, you can apply a limited function to it. So instead of looking at x, I could maybe do, is the value x greater than 5? And I would return a Boolean that I can then filter on. Or I could do the floor of x divided by the grid step to basically bucket points into where they are in a grid and partition based on that. So the idea here is these are all going to be small, pure functions that can basically be composed with the field values to actually compute the target coloring. Question over here.
This starts to sound very dangerously close to wildcards that have been the downfall of many parallel data models in the past.
Ooh, great question. So,
This starts to sound dangerously close to wildcards that have been the downfall of many parallel data models in the past. Would you comment on that?
yes, and so you're right that basically saying, hey, you can write arbitrary code to compute an arbitrary partition, and I'm going to deal with it, basically means I can't analyze these at all. And that's why these are independent partitions, right? The key idea in the dependent partitioning framework is that we make no attempt to analyze the independent partitions. They can be whatever you want. You have the full expressivity there. The place we're going to put restrictions on is the way that you can compute dependent partitions from these. And the claim is that the operations we give you there are both powerful enough to do the things you want to do, but also constrained enough that we can analyze them. And there's a very fine line to walk there. But yes, the independent partitions is basically, there are no safety belts here. You can compute whatever you want, and we will deal with it. Perfect. I meant to put that in my slide, but I forgot, so thank you. Okay, so now those are the three ways of doing independent partitions. Let's now talk about dependent partitions. And I'm a little behind on time, so I'm going to speed up a little bit. But luckily, these are actually they're not simpler. So we'll see how it goes. Okay, so the first way that you can chop up, you can compute a dependent partition of something, is to basically make restrictions of an existing one based on the indices themselves. So the idea here is we want to restrict an input space to intervals in the original type. And this is sort of hard to describe in words, so let me just do it in pictures. So let's say I've got an index space here. Again, I'm going to have the number of pieces defined by second index space. But now, instead of it being contiguous chunks or weighted chunks, I'm going to name intervals, and I'm going to do it in the standard way you might expect. Each subspace is going to have some specified extent. So I'm going to say maybe I want every 2 elements in each subspace. And then the subspaces themselves are going to be separated by a stride and start with a given offset. So here I'm saying, OK, I'm going to have 3 subspaces because my second index space has 3 points in it. And each one's going to have 2 elements. And I'm going to start, and I skip the first element, and I'm going to go by 3s. And so again, I get 3 subregions. And I can walk the strides and the extents forward to compute the colorings I want. So if what you want is regular chunks in some pattern, then this is doing it based on the indices. I've showed the 1D case here. 2D and 3D work just the same. They're just harder to draw. So again, this is most useful in the structured cases, but it actually shows up in a number of unstructured cases also. For example, Pennant, one of the codes we play with a bunch, could use this to do the cache blocking that it does. It starts with an unstructured space, but then it wants to chop it up into regular chunks to fit in the cache. And this operation works well for that. Yeah? No, a program can have as many partitionings of the same data as you want. So we're keeping the same property we had before, that you can have as many partitionings as you want. They are all effectively views on the same data. When you write to one and read from another, the compiler and or runtime does some analysis to figure out what is the actual data flow between the different children of the 2 different partitions.
What is the significance and the rationale for having IS2 rather than just having a scalar saying I want 3 regions, or 3 partitions, pardon me?
OK, so the rationale for having an index space there is several. First of all, what if I want a 2D or a 3D partition of things? If I'm operating on a 3D grid, then probably my restriction here is a 3D restriction, making subchunks in 3D. And so I could just pass 3 values, x, y, and z for that. Or I could just generalize and say it's an index space. The other important reason for it, though, comes in more irregular cases where this index space here might actually not be dense. I've shown it as dense because it's convenient, but it itself might be a sparse index space, right? It might have the values 1, 5, and 247. And I want exactly 1, 5, and 247. I don't want to have 247 new subspaces that I have to track. I just want 3. So it can be regular, and when it's regular, we optimize for it heavily, right? The dense rectangles like this, they go 1 through 3, are order 1 in size, whereas arbitrary subrectangles are order n.
What is the difference between saying 1, 2, 3 and saying 1, 5, 247?
The difference is that you got to pick those names, and so later on when you basically index into this partition to name subregions, you might want to use 1, 5, and 247. Internally, they're 1, 2, and 3.
Can you have multiple index spaces? For example, if you wanted to deal with both particles, Lagrangian particles, and structured 3D mesh?
Yeah, so each index space, each partition of an index space can use its own partition space, if you will, for naming the subregions. So I could have one. So for example, one thing we might do, and actually we do in some of the S3D stuff, is we have some partitions that are 3D and chop up by the blocks that we've partitioned around the system, and then some are 1D for like the in situ stuff. Sometimes it makes sense just to linearize it all. So each partition can actually use a different index space in this model. And then similarly, you could also have 2 different index spaces that are both one structured and one unstructured, both partitioned using the same partition space. So I might have my grid that's partitioned into 3D chunks, and then in my unstructured particles, but a partition defined on those particles that names the subsets in each of the 3D chunks. OK, this is the one that I thought was easy, but a bunch of good questions. OK, so now let's talk about the 2 that are a little bit harder to wrap your brain around, image and pre-image. And this is where folks that like fiddling around with mathematical notation will feel a little bit more at home. But basically, and I actually left the math out of the slides, but it helps if you've played with function images and pre-images before. So in particular, what image is going to do is it's going to compute the elements reachable via a field lookup. I guess the other set of folks that'll be OK with this are the database folks, because this is equivalent to a semi-join in relational algebra. And the idea is that you can apply this to another index space or partition to compute the things that are reachable from that partition. And again, I'm going to draw a picture for you in a moment. One of the key things here is that the computation of this image or pre-image, semi-joins can actually be quite expensive. They're quadratic in the worst case, although much less than quadratic in the common case. So we absolutely want to be able to distribute them and get parallelism from that. And we're going to be able to do that because we're operating on distributed data in the Legion model. So here's an example. This is one of the, I think this is a partition I computed on the previous slide of my IS1. And now what I'm going to do is I have a second index space, index 2, which is some other arbitrary index space. And I have a region using index space 1 that has a field in it, and the type of that field is pointers into index space 2. So think of this as nodes and edges, or particles and cells, or I don't know, whatever you want. Basically, any arbitrary or regular data structure. And the idea here is that an image is going to say, OK, the image of the red subregion here is going to be the set of elements in IS2 that can be reached from red elements in IS1. And so basically what we're going to do is we're going to color all those arrows based on the color of the source element. And then we're going to propagate those colors into the destination. And you know, in some cases, we get a mix of colors. That's OK. We support alias partitions. And in some cases, we get things that have no color at all, to the question before. If nobody points at it, then it's not going to be in any of them. But what we get now is a partition of the target index space that has exactly the same number of subregions as the original one. And they are exactly the ones that were reachable from the elements in there. OK? So this is great for describing partitioning on, say, you know, a graph or a tree or lists. And then the other nice thing about it is that this image operation has a mathematical meaning, right? It is the image. If I treat this field here as a mathematical function, it is exactly the image of these sets through that function, which means I can reason about it, and in particular, Regent can understand these relationships and can check the safety of assertions you make based on this at compile time. So Elliot didn't show any region relations in his talks before. You'll see some tomorrow, I believe. Elliot, we're going to do region relations tomorrow? No? OK, we skipped that. Anyway, so when you partition things up, often you'll want to capture the properties of this. For example, one of the important properties in Circuit was that when we partition it up, the edges in a given piece are only going to talk to local nodes or the ones in the ghost nodes we've defined. This is the information that's going to let you check that that's correct at compile time. OK, so for every image, there is a pre-image. Yeah?
So what going on with mixed color?
So the mixed color meant that, so that second element there is both red and green. So it's in both S1 and S2 in the second index space. OK, and that's why you note that the partition there is white instead of black, because in general, the image, even if your source partition is disjoint, the image may be aliased. OK, so pre-image, opposite of image. It computes the elements that can reach a given index space. And actually, to your question just now, this is different because it actually preserves disjointness if the target is disjoint. And it looks very similar. So here's, I think, the same picture. Now I've got some disjoint partition of index space 2. And now the same idea, except I'm going to color the arrows based on what they point at instead of where they point from. And I'm going to propagate the colors backwards to color, to compute a partition of the IS1 based on IS2. And so the idea here is that images and pre-images are the standard capture the reachability that you need in irregular computations, and that you can combine multiple images and pre-images to capture much more complicated task access patterns. To one of the questions earlier, one of the key distinctions here is that the number of things you combine has to be a finite number. It has to be something you statically enumerate. In particular, there's no transitive reachability here for exactly the problem that I can't analyze it. It's very firmly in the camp of things I would like to have, but don't know how to do it in a way that I can analyze. Although we have a collaborator who wants to talk me out of that. So we'll see where that goes. Okay, so that was image and pre-image. So this is using field data again, right? This is field data, not colorings. So these pointers here can have been computed or modified by any arbitrary legion or region code beforehand. The last is set-based operations. They're actually pretty boring. Index spaces are just set to points, so we can do intersections, unions, and differences. Either both operands can be a partition. If you do a partition with an index space, then basically think of it as an array promotion of the index space. And then the other thing you can do is you can actually do a reduction operation with union and intersection to collapse a whole partition, a whole bunch of subspaces back down into a single one. Okay, so here is the new circuit partitioning. I'm showing you the code here because that's basically all the code. There's more comments than text. And in particular, there's one call out to a placeholder for Parmetis or something here to actually compute that original partitioning. Right? Again, we want to have complete control over. We want the programmer to have complete control over how that initial independent partition is computed, but then all the rest of these are simply dependent partitioning operations that are going to compute the rest of them. And instead of walking through lines of code, I'm just going to show you this picture again from before, except I'm going to label them now. Right? So we got the wires by doing a pre-image on one of our pointers from the nodes. We then did an image on the wires through its other pointer to see what it could reach. The difference of those two was our ghost nodes. The union of all the ghost nodes is the purple shared nodes. The orange ones are actually the difference of that. And then we do two intersections to get the private and the shared. So that is, we're exactly capturing what was going on in the original code, but now that we understand it, we can optimize it, and I'll show you some performance in a moment, and we can also analyze it. And also, the programmer doesn't have to type all out. They just type the 6 commands here, and you're good. Okay. Real quick, the implementation of this is, as with many things in our programming model, is split between the various layers. The bulk of the actual partitioning operations are in Realm. This is for a couple reasons. First of all, we want it to be available to all the various ways that you can get into the Legion and Realm ecosystem. But the other thing is actually that some of these operations, specifically the image and pre-image operations, require internode communication. And by getting it down to the lowest level, we can lower the overhead. We also use the index spaces internally for copy operations and building instances. But these operations use events and deferred execution like all other Realm operations, which means that Legion is able to take care of things like mapping the fields that you specified in your commands into the physical instances, extracting parallelism in and around these operations, and of course Legion needs to maintain that index space tree so it can do its dependence analysis. And then, as always, Regions is going to provide the more productive interface for this and also do the compile time checking for the consistency of these partitions. I'm almost out of time, so what I'm going to do is I'm going to show you some performance slides and the current status, and then I'm going to leave the related stuff as kind of backup slides that people can read and ask questions about later if they want. Okay. So here's what single node performance looks like in dependent partitioning. The blue bars are the old code. So I'm showing 3 different applications here, Pennant, Circuit, and Mini Arrow. And they're all normalized to the time spent in the original code. But so the thing to note in the original code is that it's split into 2 bars, the application side and the runtime side. So nearly all the work in all the applications in the old style was on the application side, which is why we couldn't optimize it. When we move to the new model, we can optimize it, and we can also just do a few things more just inherently efficiently. So we get speed ups somewhere between 40 to 90% reduction in time on a single thread. And then if we throw more threads at the problem, we can do even better. A number of these have some sequential bottlenecks in the partitioning itself, so you don't get perfect linear scaling on a single node. And these are all problem sizes that nominally fit on a single node if you wanted. The other thing we can look at is we can look at scaling up to 64 nodes. And so now I'm using some bigger problem sizes. These are problem sizes roughly between 1 to 32 nodes worth of actual work. Pennant scales very well. Mini Arrow scales pretty well too. Circuit shows an interesting pattern where it starts initially scaling well and then starts falling off. And it actually turns out that the actual main circuit application shows the same thing, and it has to do with that all shared, all private thing is a choke point for both the partitioning style and the application style. So we've actually been looking at doing a version of circuit that is a little bit more all pairs style, but that's basically just inherent in this in the formulation of this circuit example. Okay, so the current status of this is that, as I said, we're doing it, it has pieces in all the various layers of the stack. So the realm implementation is nearly complete. The main caveat there is that the focus has been on the 1D case so far. So there's some optimizations we know we need to do for multi-dimensional cases and some of the bitmask cases. The Legion layer has an API implemented. It needs a few tweaks because I changed some things underneath that Mike hasn't caught up with yet. And there's an open question that we need to answer there about whether the mapper needs to be involved in deciding which actual field data to use if there are multiple copies. And then the Regent updates are in progress. We're working out the syntax for some cases. And the static analysis is currently done as a side thing. We need to actually dump it into the main Regent compiler so that everybody can have it. The thinking, though, is that this is all imminent. Related features, like I said, I'm just going to do this high-level version, and then I'm going to turn the floor over to Mike. So basically, these are things that are not really part of the core dependent partitioning effort, but either we knocked them out as part of the same rewrite, or they're enabled by it. One of them is the unification of structured and unstructured index spaces. There's a bunch of things that only work in one way or the other, and we're going to fix that. Basically, we're going to make everything structured, and if you don't want to take advantage of the structure, that's fine. There are some changes coming to dynamic allocation. Basically, we're still going to allow it. The way you get at it might be a little bit trickier, or sorry, not trickier, but different, and actually possibly better depending on how much control you want over things. There's an interesting problem of compaction. If I build a sparse index space, sometimes I actually want to do the effort. Sometimes I just want to operate in the sparse form, but sometimes I actually want to do the effort to figure out how to compact it into a smaller space. And so we're going to add that as a feature. And then this was the initial, the set of partitioning operations I showed just now was kind of the initial set. There's probably a few more that we can add, that we can analyze and are useful. And the other thing we can do is we can look at cases where multiple ones are used in a row and actually do optimizations that combine these individual operations into a larger operation. And there's actually a bunch of work in the, it turns out, the database community basically on the same problem that we're hoping to draft off of. So I'm going to stop there. Once we post our slides, there's a detailed slide about each of these that you're welcome to look at and ask me questions about if it strikes your interest. But we'll take one or two more questions and we'll turn the floor to Mike. Or not. OK, you're up, Mike.